Hey everyone, it's Mr. Ference. I want to talk to you today about a special situation in kinematics where we have something that is in what's called free fall. What that means is it's falling under the influence of gravity, and that's the only force acting on it, the force of gravity. So as long as you're near the surface of the Earth, within a couple hundred feet, all objects, regardless of their mass, will experience the same acceleration due to gravity. This is acceleration. So we can actually take a situation like this and we can use our kinematics equations to try and figure out what's going to happen and how it's going to happen. The acceleration due to gravity for all objects at the Earth's surface is about 9.8 meters per second squared. This is constant. This is always true. And so we have a special variable, or I guess not variable because it's constant, but whatever, letter, lowercase g, that we use to signify this acceleration due to gravity. You want to make a note of this. It's on your formula sheet. You don't have to memorize it, but we're going to be using it all the time. Pay attention to the units because this is acceleration. We can use this just like any other acceleration in a kinematics equation. Let's take a look at a sample situation and how that would work. If we have a ball that is dropped from a tower, we want to figure out, okay, how far it's going to fall after 1 second, after 2 seconds. All right. So this tells us, first of all, that our initial starting velocity is 0 meters per second. We're looking at these two particular times. Keep in mind, the height of that tower is actually not important. We don't care about it. We're just looking at the distance that it falls. So we have T1, T2. We're looking for the distance that it falls after 1 second, the distance it falls after 2 seconds. And keep in mind here that our acceleration is g, which is 9.8 meters per second squared. Okay. So the formula that we can use for this is v naught t plus 1/2 at squared. Couple of things about this. The first is that because our initial velocity is 0, this whole term just disappears. It's gone. And that's because it is being dropped. This word is a clue to you that it is starting from rest. So keep an eye out for it. It may not say it in the text like I very helpfully did right here. If something is dropped, that means it's starting from rest. So as we're solving for x1, this is 1/2. Remember, our acceleration is g. It's 9.8. So that just becomes 9.8 meters per second squared. Our time is 1 second, and that whole quantity is squared. 1 squared is just 1. 1/2 times 9.8. We get our answer that after 1 second, it has fallen a distance of 4.9 meters. Okay, cool. For the second part of this, it's the same equation. The only thing that is changing is we're putting in a different time for t. Here, 2 seconds. So 2 squared is 4. This is still 4.9. 4.9 times 4. That is 19.6 meters. So after 2 seconds, it has fallen a total distance of 19.6 meters. Now check this out. The distance it is falling in these second long intervals is changing. It's not fallen 4.9 meters every second. It's falling a greater amount because it's speeding up. Now, okay, like duh, like objects that are falling get faster as they continue to fall. But it's really neat, I think, to see this in the math as well. Let's actually look at how the velocity is going to be affected as something falls under the influence of gravity. Now, let's imagine that instead of just dropping it, I am actually throwing a ball up in the air. So its starting velocity is not 0. It's actually 19.6 meters per second. And this is traveling upwards. So this is positive 19.6. Gravity here, the acceleration due to gravity is, I'm going to call this negative 9.8 because this is always acting downwards towards the center of the Earth. And this is constant. So the entire time that the ball is in the air, its acceleration will be negative 9.8 meters per second squared because it's down. Okay, so all we need to do to fill in the rest of this table is just understand that the velocity is going to decrease by 9.8 meters per second every second. So it's starting off going up at a speed of a velocity of 19.6 meters per second. After 1 second, it's 19.6 minus 9.8. So this is 9.8, positive 9.8. So it's still going upwards. It's still traveling up, but it's starting to slow down. All right, at 2 seconds, 9.8 minus 9.8, its velocity is 0. Okay, weird. Let's keep going. After 3 seconds, 0 minus 9.8, now it's negative 9.8. That negative tells us now that the ball is moving downwards. It's starting to now fall back towards the ground. And then its final velocity, negative 9.8 minus 9.8 is negative 19.6, traveling downwards. Okay, let's pick this apart for a second. What this is telling us is that as something is traveling up in the air, it continues to travel upwards, but at a decreasing speed. It reaches a point where for an instant, for a split second, its velocity is actually 0. And that's because it's that's the sort of turnaround point where something stops moving up and it starts moving down. Okay, just for a tiny fraction of a second, its velocity is 0. After which it starts moving back down at an increasing speed. In other words, what this is saying is, so this is what I love about physics. We can work through the math and we get an explanation of what's happening. And then we actually do the thing in the real world and we observe exactly the same thing. This is what's awesome about physics, to me at least, is we can examine the real world using math and we can actually get the correct predictions of what's going to happen and why it's going to happen. This concept, this sort of thing that we just did, this tells us 3 important things, okay? The first thing is that at the highest point of that trajectory, the highest point in that path, which we call the apex, that's the sort of turnaround point. At that apex, just for a tiny, tiny fraction of a second, the velocity is actually 0 meters per second. The second thing that this tells us is that, assuming that it's coming back down to the same height, this projectile, this thing that's in free fall, is going to come back down with the same speed with which it left. Now, I say speed here, not velocity, okay? Because as it's going up, it's positive 19.6. As it's coming down, it's negative 19.6. But the speed is the same. The number is the same. This is why it's dangerous to fire guns into the air. The third important thing that this tells us is that if we ignore air resistance, which we will, the path of a projectile is symmetrical. So it has this symmetry. What I mean by that is that the going up part is mirrored by the coming back down part. So assuming that it's coming back down to the same height, the time it takes to go up is exactly the same as the time it takes to come back down. And the speed that it has as it goes up is the same as the speed it has when it comes back down. These are really useful things to keep in mind as we start working through these problems. So you are now able to go through and solve the free fall part of your problem set. Just keep in mind, this is acceleration. It works the same way that you've been doing it. It just now we have this number that is always going to be the number when we're in free fall. So good luck. Let me know if you have any questions and I will talk to you later. Bye.